Thank you very much, and I appreciate the opportunity to be able to give a talk here. So it was known for a while that braided non-degenerate categories, so which is pretty much the same thing, modular categories, serve as a model for topological order. So this is an exotic quantum state of matter. And I mean, there is a paper of Kitaev and Kong from 2011. There are other people certainly who contributed to this correspondence. So let me maybe start with a short dictionary, so to say, that explains how this are related. So a non-degenerate, braided, or modular, I'm going to use these words interchangeably because it's pretty much the same, corresponds to the bulk topological order. So simple objects of the category correspond to any types, to quantum particles. There is operation of tensor product, which is sometimes called fusion, so it corresponds naturally to fusion of anyons. And that, by the way, motivates the name. So these categories are also called braided fusion categories. So the fusion rules encode how simple objects decompose after tensoring. So this is known as fusion rules. So this is Nij, I, J, and K are labels of simple objects, and Nij, K are non-negative integers. Now, the most essential part, of course, of this category is associativity constraint, which corresponds physically, I believe, to the process of changing the fusion order. So you can first fuse X and Y, and then the other way around. So this can be encoded as a system of what is called 6J symbols, which results in a rather complicated and nonlinear system of equations. So there are creation and annihilation operators that involve duality in the category. There is braiding that involves permuting objects X and Y, and that I think corresponds to exchange statistics, if I use this term correctly. Finally, non-degeneracy, which is a key property of such categories. Mathematically, it says that the only simple object that has trivial squared braiding with everything else is the identity object. So physically, the state correspondence statement is that there are no non-trivial transparent objects, or equivalently that braiding detects every anion. I'll continue this correspondence later on as talk progresses, but at this point, are there any questions? Okay, I need to make a disclaimer. I'm a mathematician, okay, so my intuition is on this side. Okay, but I did interact with physicists quite a lot, and I learned this dictionary, but as with every foreign language, and I don't mean English, but learning vocabulary is not really learning language. So if I say something which is does not make physical sense, please correct me or just take it easy. All right. So let's see. Okay. So how can one think about braided fusion categories? Now, of course, one can take this as a definition once the proper axioms are introduced. But I think a useful thing would be to understand what are the simplest examples. So the simplest example is what is called, I believe, abelian anyons. So this corresponds to a category where objects form an abelian group, right? Necessarily abelian, because otherwise there is no twisting, there is no braiding, there is no permutation. Furthermore, so let's say I'm going to denote objects of this simple objects or anyons, just they correspond to elements of the group. And now to any element of the group, you can assign itself braiding with itself. Okay? So this is a non-zero scalar. So furthermore, so let's call this Q. Now, the hexagon rules of braiding imply that Q is a quadratic form. Meaning that this ratio is a symmetric bilinear non-degenerate form. Again, everything that will happen today will be non-degenerate. So this is the only type of braided categories I'm going to pay attention to, and the Qx is Q negative x. Now, it turns out that this is the most general example of such a braided category in which every object is invertible. So this is a typical example of, well, I'd like to say abelian theory. Is this the right terminology? Okay. All right, and so that's a result of Joyal and Street from long ago, from 1980s. Now, if anything, this brings a certain geometric flavor into this theory, because quadratic forms are studied in linear algebra. They also allow you to talk about things like orthogonality, for instance, right? Which is not apparent, just from the definition of braided category. To see this in general, so what we mean by orthogonality? So two objects, let's give this a name, bx, y. So this is an analog of inner product. So two objects are orthogonal if this is trivial, if this is 1. So in general, we have a non-commutative version of orthogonality, namely, you have this condition that the squared braiding of two objects to anyons is identity. Now, because category is non-degenerate, it cannot be just universally true for a given x, but it might very well be true for any specific pair of y and x, right? So this can be thought of as categorical orthogonality. Again, this certainly has physical meaning. It means that that two particles loop one around another, and nothing happens, so nothing measured, right? Okay, like I said, it's a foreign language for me. So okay, now of course there are braided categories with non-abelian anyons. So non-abelian examples. some of those are very well known. So one is Ising category. It has three simple objects, one, let's say tau and x, and the fusion rules are x tensor x is 1 plus tau, and tau tensor x is x, and tau tensor tau is 1. Oops, sorry. So this, of course, here are 1 and tau are abelian, x is not. Its categorical dimension is the square root of 2, as can be seen from this. Another example is so-called Fibonacci category. So these are the simplest ones, Fibonacci category. And that has only two simple objects, 1 and x, and the fusion rules are this, and then the reason it's called Fibonacci because the categorical dimension of x is the golden ratio. Now, more generally, there is a big supply of interesting braided categories, go by the name of Verlinde categories. So the way they are constructed, they depend on two parameters. One is the simple algebra, and another simple algebra, and Ale is non-negative integer. So this can be explained in many ways. One way is to via representations of affinely algebras, another via certain simplification, semi-simplification of representations of quantum groups at roots of unity. These two examples correspond to the choice of G SL2 and some small value of L. Another basic example is what is called the Drinfeld double, the center. Drinfeld double of a fusion category A. So fusion category is pretty much the same thing, except that there is no braiding. So there is no commutativity constraint. So this is denoted ZA. It's, in a sense, parallel to the notion of the center of a ring, because one, of course, has every right to think about braided categories as analogs of commutative rings. So fusion categories are just analogs of arbitrary rings, and this is the center. So one example, I think, which is particularly relevant to what I have on the board here is known as a toric code. Now, with this notation that I developed, I can describe it in two ways. So I did not give a name to this, but let me denote it like this, CAQ. So here A is a abelian group, and Q is a non-degenerate quadratic form on it. So toric code can be understood as category with the group of simple objects Z2 cross Z2, and the quadratic form being the hyperbolic form. And another description is that this is just the center of Drinfeld double of the category of representations of Z2. Any questions so far? Again, it goes under the special name because this is a particular model was well studied by physicists over the years, and pretty much every talk I heard has mentioning of that. Okay, moving on. So before that, a comment. So, well, I mentioned 6J symbols, like, the first thing when I defined it. In a sense, 6J symbols are not that efficient. Like I said, they, in general, result in a very complicated nonlinear systems. And after all, this is not the best way to study things in representation theory. Just think about representations of a finite group, then describing its 6J symbols is quite a computational task, but that's not how we usually study representations, right? Okay, so how do we study representations and what are they? So rings act on modules. That's, of course, a routine theme in basic abstract algebra, but similarly, tensor categories, or in this case, let's say braided categories, act on what is called module categories. And the definition is completely parallel, namely a module category M over a braided category B consists of a linear semi-simple category, and this module action, a functor satisfying some natural coherence similar to that of a pentagon equation. Or equivalently, there is a functor from B to the end of functors of M. So know that if you have a linear category, then its end of functors can be composed, right? And this composition plays the role of tensor product. Okay, so this is just analogy between module and representation. Now this has, of course, a different chalk for that. So this also has physical interpretation. So here I'll continue this table as I promised. So B module category M corresponds to what is called gapped boundary of a topological phase. And there are a couple of things that you can introduce here right away. Namely, once you have a module category, you can consider the dual category. Namely, I'll call it like this, B star M. It's a category of B module and the functors of M, so which has the name of dual category, but please note that we can associate such thing with every module category. So the same category can have many duals. So here, the dual is goes under the name of boundary excitations. So again, I'm pretty sure everyone in this room has better way to think about this, but well, so what happens? So the anyons reach boundary and then something happens to them. Okay, so now on the boundary, in general, they can be fused with each other but not braided. Okay, so unlike this category B, this one is no longer braided. It might be braided. I'll talk about that. Okay, so now what we do with this? Of course, it's an interesting a natural question to try to understand all module categories over a given B, or in physics, to try to classify or at least understand those that you know, boundary conditions. So here is something which is now categorical and purely categorical in the sense that it does not have a ring theory analog. So this is a construction which is called alpha induction, and it was considered by several groups of authors. It's Bokenhauer, Evans, Kawahigashi, and also Fuchs, Runkel, and Schweigert in more physical context. And it goes like this. So, well, we have a map, a functor from B to the dual category of bimodular and the functors of M, which sends object X to, say, left multiplication by X. Now, because category is braided, this is going to commute with the B action. Just imagine something from B acting here on the left. You can braid it with X, right? Yeah. And so this is a module action. But the interesting thing is that to make this bimodal functors. So what I'm saying here, we want to be able to commute it with an action of an object y from B. So here y is in. Well, there are two ways. You can use braiding, but you can also use the reverse braiding. So we can use, yeah, correct, sorry. I think X and Y need to be changed like that. Yeah. So we can use either braiding, just, oh, guess YX in this case. Or, well, the thing about this, that in the non-degenerate case, the braidings come in pairs. Namely, you can have this and this. So both of them go from y tensor x to x tensor y. But they do not have to coincide. In fact, when category is non-degenerate, they're quite apart from each other. So you have two functors. And then I'll call them alpha plus minus m. That was the notation introduced. So again, let me try to say something physical. So, well, okay, I'll say something which is probably silly. So a particle can approach boundary like from two sides, let's say from the left and from the right. Okay, and then it kind of interacts with things on the boundary, but it really depends where it came from. All right, so this corresponds to positive and the negative braiding. Leon, does this sound right? Okay, that's reassuring. I need lots of reassurance here. So two orientations, okay? So let me add this to this nice table. So alpha inductions, alpha plus minus m from B to the dual. And so this would correspond to two possibilities of bulk boundary couplings. again, I'll try to describe this as approaching boundary from different directions. Okay, so now it turns out there are this turns out to be quite important notion, this alpha induction. And so here is the first. I mean, they're important physically, I understand, but here is something, a theorem that was established basis of them. So this is a theorem, and the informal description of this, that's a slogan I heard from Zhenhang Wang, that symmetries are defects. Again, I cannot really assess how reasonable this is physically, but it sounds kind of a postmodernist, type of of a statement, and that's enough for me to like it. Okay, so now in order to explain this, let me just say that if M and N are bimodal categories, then there is an operation of tensoring them over B. And mathematically, it's not different from tensoring two modules over a ring. You can define it by certain universal property. So what it means physically, well, physically, I understand every tensor product is sort of a fusion. So this is fusion of boundary of boundaries or boundary conditions. So what one gets, of course, is another bimodal category, which is again does not have to be braided, but there is a special class of module categories that are particularly interesting. So we say that M as above, bimodal category M is invertible if the dual category, that's the thing I introduced, right? So the category of bimodal and the functors of M is equivalent to B. So such things, I believed, are called invertible domain walls. So I'm not quite sure about the appropriate terminology here. So the way I use it is that boundary condition is a generic name for a module category. Domain wall is used in a more restricted context as invertible module category. Okay, so now such categories, of course, are closed under the product operation. So what they form, so this form a, well, in fact, categorical group called the Picard group of B. So it consists of all invertible bimodal categories with the operation of tensoring them, which yields another module category. So that's one group, which you can call the group of domain walls or the group of defects. There is another thing. So now B itself, corresponding the modular categories corresponding to the bulk topological order, can be studied for its symmetries. So odd braided B is the group of braided equivalences of B, which think appropriate physical descriptions of global symmetries of the bulk. Now, in view of what I said before, that the basic example of a braided category is an abelian group with a quadratic form, it's quite natural to think of this as an analog of the orthogonal group. In fact, the classical split orthogonal group can be realized as the group of braided equivalences of the Drinfeld double. So now this, is, of course, is a very small example. Here the orthogonal group is just Z2, the group permuting to bosons in this category. And so the And so there is turns out that these two groups are isomorphic or equivalent if you view them as categorical groups. This is a theorem by Ettingov, Vostok, and myself, saying that these two groups associated to non-degenerate category B are isomorphic or equivalent if you are categorically minded. Let me explain where this comes from. So it turns out that there is a very natural map from left-hand side to the right-hand side, and then there is some work involved in showing that's an isomorphism. So this has to do with this alpha induction that I have on the board above. So not a proof, let's say reason for that. If M is an invertible bimodal category, then the two alpha inductions from B to the dual category are in fact equivalences. Because this is, of course, just B. But this is equivalent to the definition of being invertible. They are equivalent, or isomorphisms. Well, they are very different from one to another. Okay, because braiding and its reverse are very different. So what one can do, one can take, let's say, one of them and compose with the inverse of another, right? So they both go from B to the dual. If you take this composition, then this is a functor from B to B. Let's call it maybe sub M. Okay, and that's in fact an equivalence, and in fact it's a braided equivalence. Okay, so this is somehow easy direction. The difficult part is which I'm going to skip, is that every equivalence appears in this way. Okay, so now why do we care? Well, I can tell you what our motivation was. You see, this category, although it kind of defined in very natural terms, this group has a problem that it's, the definition of the product is via a universal property. So it's hard to compute in practice. On the other hand, so these are just functors, or like I said in the examples, like orthogonal groups. So these things are easy to compose because if you have two orthogonal maps, then their product is just a composition. Okay, so this is an advantage. Okay, so which allows you effective computation of the Picard group. So an application of this, which is also made more feasible by means of this isomorphism. So application we can consider the central G-graded extensions of B. This is closely related to the procedure called gauging. So here a G is a finite group. So it turns out that such extensions are parameterized by certain functors from G to the Picard group. Again, the right gadget is monoidal to functors. And again, although this is, can be compactly stated, the difficulty is that it's hard to construct these things because multiplication here is difficult, but in view of this theorem, we can reduce it just to the compositional functors, or like things that happen in the orthogonal group. Faithfully correct. Yes, okay, so, well, very good, but now, as we know, not every module category, of course, is invertible. And so there are interesting, so beyond invertible module categories. So again, in terms of this dictionary, this would be non-invertible boundary conditions. Okay, I'm happy. Surface. It's just one of the, yeah, EM duality, yes, yes. Okay. Yeah, so, okay. I mean, all right, how about this? Like, in order to be less confusing, I will just talk it, in my language. I just call them module categories, and you can, interpret them in the more in a more correct way. So now that you mentioned toric codes, so for B, how did we call it? Well, let's see the center of Z2, the toric code. Okay, so as Matthew mentioned, so the Picard group is very easy. It's just Z2. And it has, of course, the identity and the, well, and this is what is called, let's say, EM duality. Okay, so the only non-trivial invertible module category, but there are also 4 non-invertible ones. So there are 6 altogether. And so, well, it's not hard to, come up with a 6x6 multiplication table, but what is desirable is to have a statement similar to this theorem. So again, with the same agenda, because we like that we are able to compose braided equivalences. So can we replace the right-hand side of this by something that can still be easily composed? And okay, I can only come up like with the mathematical statement without, completely embarrassing myself. So it has to do with the subgroup structure of Z2 cross Z2. So let's see, what are the subgroups? So there are the trivial subgroups. Then there are 3 copies of Z2 sitting inside. and there is Z2 cross Z2 itself. But now this thing has a non-trivial second cohomology class. Two cohomology classes. So the invertible ones, they correspond to the trivial one and non-trivial cohomology class. The other four here are non-invertibles. What is their physical meaning, if any? I honestly don't. Okay, so this is tutorial code, right? So with this hyperbolic form. Yeah, that's right. Condensing, like, let's say, the copy of Z2 consisting of trivial object and the fermion. That's one way to think about it. Okay, right. So, and there is a generalization of that. So, well, we still have two copies of the alpha inductions from here, from B to the dual, but in case when M is not invertible, so they are no longer equivalences. So the trick, I did erase it. No, I didn't. Okay, so here are like this thing where see, I'm very excited about this. This thing, when we multiply one of them with the inverse of another, does not work. But what we can do, of course, is to replace the inverse by the adjoint. Alpha plus M adjoint. Now the price for that's still a functor from B to B, but it's no longer a strict tensor functor. It's what is called a Lach tensor functor. And what it means is that you have this tensor structure, but it's no longer an equivalence. It's just like a map. Okay, and it's also braided. It respects braiding. There are a couple of additional properties. So it's also a collax, meaning that there is an arrow in the opposite direction. Again, not an isomorphism in general. And the general name under the which this functors appear, I think is the name is the Frobenius functor. So it consists of such a functor which is braided and have like these two structures in the opposite directions compatible with each other in a certain way, resembling that of resembling the definition of a Frobenius algebra. And so here now we have an isomorphism between B module categories. Again, thought of as a ring, maybe ring isomorphism, and this I call it like so Frobenius and the functors of B. Again, well, I'm going to elaborate a little bit on that, but well, first of all, it does reduce to this theorem relating the Picard group and data equivalences. Okay, and again, such things, once you construct them, that's the rule of composition is easy, but how can one think about them? So one can think of such functors as partial symmetries. So what I mean by that? Let me explain. So partial symmetries of B. Well, again, classically speaking, that imagine that you have a space with a quadratic form, but then you identify not the whole space with itself, but just a part of the space with possibly another part of the space, something like partial isometry. Okay, so here how it works in general. So given a commutative, appropriate commutative algebra in B, there is a category of local A modules in B, which is denoted as B A local. So what is this exactly? It's, well, I'd like to say this is the condensation corresponding to this algebra A. Now, to avoid possible confusion, I realized that the term condensation is used in two meanings, okay? So first of all, you can take just all A modules in B, and that's a fusion category, not necessarily braided. But then inside this braided category, there is, inside this fusion category, there is in fact a braided subcategory, okay? So, right. So which corresponds to a new topological order that is obtained by means of this condensation. And so in this sense, these partial isometries, they correspond to equivalences, let's say, between two possibly different localizations. Okay, think about this. So if A1 and A2 are trivial algebras, this is nothing but an equivalence of the original category B. Now, as long as A1 and A2 are non-trivial algebras, well, that's no longer, a map from B to itself, but rather a map from localization of B to another localization of B. Okay, so and it's an interesting problem given a braided modular category B to study all its possible localizations. Okay, so it can happen that there are none, or it can happen that there are few. Okay, and so so A1, yes. So A1, A2 are commutative algebras. So, well, for any algebra, there is this construction of local modules, okay? So those that inherit braiding from the braiding of B. Now, it can happen that certainly if you take the same algebra, then there will be equivalence. It can happen that you take different algebras, and there is an equivalence. So that's what I call partial equivalence, maybe like residual equivalence is a better word. I'm still no, between the localizations with respect to A1 and A2. A1 and A2 do not have to be isomorphic. Does that make sense? That's exactly what I wrote here. For example, yes. Yeah. That's correct. Well, not the category itself, but rather the equivalences, between these localizations. That's partial symmetry. Now, the story code, story code is, in the sense, is not very interesting because it only has, a part of the trivial localization just itself, right? It has the two that you mentioned, yes. Okay, so, and this does give rise to this non-invertible things. Okay, so now, so what I was saying that right. So in fact, another way to think about all this business and this theorem in particular is that one can parameterize bimodal categories, invertible or not, by triples, where A1, A2, and let's say phi between localizations. So where A1, A2 are commutative algebras, and this is what I called the partial symmetry. Again, it can be interpreted, as a functor from B to itself, but no longer tensor, okay? In which case it makes more sense. It's really sort of a symmetry of B. So now, it turns out that you can study, the kind of the higher fusion rules, like the way these things decompose into irreducible bimodal categories. So there is kind of like think about like higher version of Grothendieck ring, right? In the usual category, you tensor two objects, you decompose them into sum of simples. You can do the same here, and that's a different thing altogether. Even like in this example with the toric code, it's not. It's not a semi-simple algebra anymore, but it turns out that you can have a certain like partial order of it on this some gradient by certain partially ordered set, which has to do with these localizations, because you see localizations can be ordered. You can say, like so, let's say localization x is bigger than localization y if y is the localization of x and so on. So there is certain lattice. Okay, so this lattice induces a certain gradient, again, not in the sense of a group gradient, but in the sense of gradient by the partially ordered set. So there is kind of additional structure here that is closely related to this localization business. Yeah, I guess I'll stop here.
So these invertible defects actually have some very physical meaning in the sense that wave function or something like that. It's never reflected, it just goes through. And these partial, these non-invertible ones, what would happen? The physical meaning would be that completely reflected or partially reflected. Is that something or a meaning of it?
Okay, well, it will, again, it reduces to this, like, to the good situation that you described, like where everything is reflected, but for the new, and in a sense, for a new topological order, for this reduced one.
Like in a pricing model, you could say open boundary conditions, but open boundary conditions is just a special type of defect. That's not invertible.
Well,
which one would that be in whatever?
Well, in Ising is not like a good example, because in Ising there's only one module category, the Ising itself, right? So, well, think about like what happens in toric code when you condense a single boson, all right? So, you pass to the dual, but that's no longer, the same thing, right? So, I mean, again, you probably will tell me what happens there. I honestly don't know, but again, my attempt was to try to reconcile, this theory for invertibles with those for non-invertibles, because both are, I mean, mathematically both are interesting.
Sorry, how is different than Maastricht's theorem? Will that just say B model categories? What's the actual attribute?
Again, what are Ostrix, which part of the board you are referring to? This? Well, it's different from Ostrix theorem, for example, in respect that Ostrix theorem produces, first of all, it works for any category, braided or not. It produces an algebra in that category. Okay, so here the situation is different. So what I'm saying only applies to the case when B itself is braided. In this case, you produce a pair of algebras, but these are commutative algebras. Okay, and the difference is huge because commutative algebras are much easier to come by. All right. So the difference is that, this gives you kind of geometrical interpretation of what happens in braided case. Right. Okay. I'll try. Yes. So let's see. I'll erase this part here. So let's describe this a little bit more in more detail. So again, B, this modular category, consider the following set. I call it XB. And it consists of the following things. So C, this is our equivalence class. Such that C is a localization of B. Okay, so this set is at least non-empty because, if you take trivial algebra, then, there is B. But there can be many others. So then there is a partial order. So this XB is partially ordered, namely, we can say that the C is bigger or equal than D if D is localization of C. So localization is a transitive procedure, right? So you localize once, you localize the localization, it's localization of that thing. So this is somewhat similar to the lattice of subgroups of a group. Okay, that's a good analogy to think by. Okay, and so now, according to this, parameterization that I have, so we can assign to every M an element of XB, namely the class of this localization, right? So you have this or this, they are equivalent, so it does not matter which one you assign, right? So, which means that, the set of indecomposable module categories is partitioned according to this localization, what localization it yields. So, maximal element here will be, of course, B itself, right? And the things corresponding to this maximal element are the equivalences. All right? So then the grading I mean by that is the following. So if you have M, let's say, in C1 and N in C2, and you tensor them, then the result is a direct sum of some categories, I don't know, let's say K, with some multiplicities M and K, but where a K is in D, and D is less or equal, less or equal than C1 and C2. I hope I got this inequality right. So this sort of grading, right? So, it's not a group by any means, but it's a partially ordered set. So you have this grading of filtration if you prefer, right? So there is some structure here, which is kind of not surprising because, you know, like orthogonal groups and like related kind of decompositions, that's a highly structured thing. So we are trying to replicate this in the setting of braided fusion categories rather than just orthogonal spaces.
So in the case, the G-graded case,
Yeah.
maybe I think it's also your work getting
That's right. My Oettinghoff is Oettinghoff Ostrich, yes.
you have these results on topology.
That's correct, yeah.
You have something to say.
Right. So, well, okay. No, this is like a part of this program. So, you know, the reason for us to study graded extensions is that we were worried, I mean, back then, that there are not sufficiently many interesting examples, right? You know, some people constructed it by 6G symbols, Tambara Yamagami. We wanted conceptual understanding of that. Now, yes, there is a cohomology. There is lots of kind of hidden, you know, in this gadget, you know, there are kind of cohomology abstractions, but at least it's something we understand. Now, suppose that we want to do something more general. So we want to consider extensions which are no longer graded. Okay, so you kind of centrally embed B into a larger interesting category. So such things I actually studied quite a bit. They're called exotic for the reason that people have no, you know, like maybe you heard like things like Hagerup category and so on. So these are these things. You know, this is just done by brute force. So, but let me write this here. So, but you see, like if you have an extension, let's say B inside, I don't know, C, where C is no longer G-graded, then C is a B module. In fact, it's more than that. It's just pseudo-monoid, right? Because there is an algebra structure, you know. So B module like algebra, higher algebra. So if we learn how to construct this, we will be able to conceptually describe all these exotic constructions, which I don't believe exotic, is just the lack of our understanding. So, well, how to do it? Well, we'd like to understand what modules over B are, right? And how to construct like algebra objects, like beyond the graded case. So my expectation is that there is an analog of Hochschild cohomology, you know, which can be probably computed, at least in some cases using this description. So it's in terms of like associated functors. In terms of the associated functor, so to every module, the associated functor, and that functor will, in this case, will be what is called a monad, you know, so there will be kind of multiplication there. So that's the hope. We didn't get very far with that yet.
Suggest some kind of a generalization of the last one.
Yeah. Okay. Well, it's good. We can talk about this. But one thing, perhaps, that it's a resemble, which is known, there is a notion of a modular invariant associated to module category. So modular invariant is this thing. To M, you associate a certain square matrix modular invariant. And it's called modular because it commutes with the representation of the modular group. This assignment is multiplicative. So the M tensor N is in fact the M times the N in terms of matrix multiplication. So now this is a categorical extension of this result. Because to every functor, you can associate its graph. Right? You know, just take like image of X and see how many times Y occurs in this image. You'll get an integral matrix there. So if you will, this ZM is, you know, like kind of linear algebra counterpart of this categorical gadget. So as long as modular invariants have meaning, so this has meaning as well. Yeah. It's pretty much the same, I think, like, so, yeah. I think, this can be just translated from one language to another, so, yeah. But again, it's nice to know that there is a kind of categorical thing behind this, yes.
Yeah, on these partial symmetries, like the boundary changing operators in your like bulk boundary like situation, where you have like the bulk is the same, and then you have two types of outputs. The partial symmetry goes between those.
Yeah.
Is that what you had in mind?
Kind of, almost.
But again, it's not symmetry of algebras. Algebras can be quite different. It's a symmetry between their models.
Marvelous. Thank you again.
Thank you.